All right, everyone, welcome to another seminar in our ACOM seminar series. Today, we're coming to you virtually, and our speaker today is Noah Stanton from York University, Canada. Noah's a bachelor's in environmental biology from McGill and in earth and atmospheric sciences from York, and is now a graduate student at York with advisor Neil Tandon. And this is an interesting and timely talk today. So internally, we've been evaluating a lot of different configurations of CESM, including simplified chemistry, to assess them for community use and to figure out how we can continue to support these things in future model releases. But I think, as you'll see today, model hierarchies can also provide a lot of scientific insight into some of the things that are important for our climate system and its impacts. And so today, Noah's going to share some work exploring how tropospheric chemistry affects climate in CSM2. And I will just remind all of our viewers on the live stream that if you have questions, please enter them into the Slido application below the live stream, and we can address those at the end of the talk. So Noah, take it away.
Thank you, Nick, for the introduction. Good afternoon, everyone. As Nick said, I'm here at ACOM to present my work done during my master's that I completed at York University in Toronto, Canada, under the supervision of Neil Tandon. So as the title says, Neil and I asked the question, how does coupled tropospheric chemistry affect climate? That is quite the lofty title, but luckily we were able to use the wonderful tool of the Community Earth System Model version 2.1.3 or CESM2 to begin to answer that question. The wonderful folks at NCAR have been developing this framework initially from the climate community model all the way back in 1983, and they began the CESM project in 2013. So now with advances in computation, we can begin to probe these sorts of lofty questions. But why is it important to improve our understanding of these processes? I'd like to bring to your attention just figure one. The IPCC assessed contributions to observed warming from 2010 to 2019. That is present in the newly published AR6 report. We can see a number of chemical atmospheric constituents like carbon dioxide, methane, VOCs, different types of aerosols, etc. Constituents that contribute to warming, like carbon dioxide, are seen in red, while constituents that contribute to cooling, are like sulfur dioxide, are seen in blue. The error bars on many of these constituents are quite large, with some error bars straddling across the zero line. Black carbon is an example of one of these constituents that is considered to lead to warming, but the uncertainty of that is quite large. Coupled tropospheric chemistry has a direct impact on most, if not all, of these constituents. It's also important to note that this assessment is relative to a baseline historical climate from 1850 to 1900. In order to accurately assess this parameter, climate modelers must ensure that our historical simulations of climate are as accurate as possible. Understanding the impacts of improvements to coupled tropospheric chemistry on climate, i.e. the radiative process, dynamical feedbacks, etc., is crucial to understanding the underlying mechanisms involved. One recent improvement to CESM2, WACM6, pertains to volatile organic compounds and organic carbon, specifically secondary organic compounds. So what are the chemical processes that contribute to the formation of secondary organic compounds? Biogenic volatile organic compounds, BVOCs, are an important precursor to secondary organic aerosols, SOAs. BVOCs are emitted by a number of plant species, including flowering plants, ferns, conifers, and bryophytes. Isoprene, the structure of which is seen in figure 2, represents about half of the 1,000 teragram per year emissions of BVOCs, and predominantly comes from broadleaf deciduous trees, like the fig tree seen with the number 4 besides it on the left side of the slide. Monoterpenes and sequesterpenes make up much of the remaining portion of BVOCs, and mainly are emitted from conifers, like that seen with the number 3 besides it. And this is just to really depict that there is quite a regional difference in the composition of BVOCs. BVOCs are highly reactive with atmospheric oxidizers like OH, O3, NO3, etc. Figure 3 shows how isoprene generally has the lowest reactivity in SOA yields compared to monoterpenes, sequesterpenes, and diterpenes. With that being said, isoprene with its high global emissions is the primary precursor to SOA. The oxidation of BVOCs and VOCs in the atmosphere leads to the production of SOAs. Biogenic SOAs make up the majority of global SOA loading. The oxidation reactions are typically initiated at the double bond in the VOC, creating a peroxy radical. In figure 3, this step is seen with the RH plus OH, ozone, etc. step. These peroxy radicals can then react more than through further oxidation reactions with HO2, RO2, NO3, etc. Eventually, these products can condense into aerosol. Another interesting process that occurs with VOCs is ozone formation in the lower troposphere. And so typically in polluted conditions, when VOC to NOx ratios are between 4:1 to 15:1, you get ozone formation, with peak formation occurring at a ratio of 8:1. The reactions that lead to this are shown on the slide with TR1, TR2, and TR3. Another subset of SOA that I'd like to talk about is organic nitrate aerosol. Figure 4 shows a simplified diagram of the formation of organic nitrate from nitrate and BVOCs. Organic nitrate contributes to the formation of SOA, especially at nighttime, due to the vampire radical NO3, which is in higher concentrations due to the lack of photolysis and a reduced NO sink. Some studies have shown that the total nitrogen budget, NOI, can be about 30 to 45% organic nitrate in the particle phase. The inclusion of nitrate BVOC chemistry in models has led to a 50 to 70% increase in SOA yields in European modeling studies. Observational studies generally underestimate organic nitrate's influence on SOA formation due to its short lifetime when there is sufficient BVOC and NOx. Organic nitrates in both the particle and gas phase are known to contribute to the formation of brown carbon. Brown carbon consists of SOA, humic-like substances, organic nitrates in the gas phase, and organosulfates, all of which are subsets of SOA. And there are some other constituents in brown carbon. Brown carbon is primarily comes from biomass burning, and it is distinct from black carbon due to its optical properties. Brown carbon has a spectral dependent absorption, smoothly increasing from shorter wavelengths, visible wavelengths, to the UV, whereas black carbon strongly absorbs across the whole solar spectrum. Brown carbon is known to lead to increased absorption in the troposphere, with brown carbon estimated to have about a 0.04 to 0.11 watts per meter warming at the top of the atmosphere, with about a negative 0.06 to negative 0.14 watts per meter cooling at the surface. There is a large uncertainty with this value. Brown carbon has significantly increased from 1850 through the 20th and 21st centuries. So with that brief introduction to various aerosol properties, I'd like to get into the nuts and bolts of what our investigation was involved with. So the main tool that we used was the Community Earth System Model 2, as has been mentioned in the title. It was chosen for this research as it's open source and has extensive documentation support. CESM consists of these 7 components, which I'm sure you all know of, with a coupler in between them, communicating with all. The output for this study predominantly came from the atmosphere component, the whole atmosphere community climate model 6, or WACCM 6. WACCM 6 captures a large number of atmospheric chemical pathways, all the way from the Earth's surface to the lower thermosphere. There are 70 model levels, with a model top of an atmospheric pressure of 4.5 times 10 to the negative 6 hectopascals in a hybrid sigma coordinate system. WACCM 6 has 231 freely evolving chemical species with numerous chemical pathways for the whole atmosphere and detailed SOA chemistry. Specifically, they added a 1D VBS modeling set for the newest iteration of WACCM 6. WACCM 6 also implements the modal aerosol model, MAM4, that captures many chemistry-climate interactions. These interactions can be seen in figure 6. WACCM 6 also has a fully coupled ocean, which until recently has been computationally prohibitive alongside the coupled tropospheric chemistry. This allows us to investigate questions related to tropospheric chemistry's impact on climate without having to prescribe sea surface temperatures. So we get this important sort of coupling facts that happen between the atmosphere and the sea surface. There are 2 case configurations: the BW1850, the full atmosphere case, and the BWMA 1850, the simplified chemistry case. BWMA 1850 only has coupled chemistry in the middle atmosphere, which is the stratosphere and above, which does not include tropospheric coupled chemistry. The middle atmosphere chemistry set is most similar to Wacom 4's chemical mechanisms, with the addition of the metastable ions O plus 2D and O plus 2P. Calculations of the output were taken from 100 years of simulation time over a 1.9 by 2.5 degree lat long grid. Both of these configurations are control runs with human emissions fixed to pre-industrial levels, i.e. 1850 CE. Both of these configurations had prescribed cyclic QBO forcing, QBO being the quasi-biennial oscillation, which is a stratospheric oscillating wind in the tropics, to properly constrain the output. The analysis consisted of calculating long-term spatial and zonal means and performing a mean difference between the two configurations for a number of climatological variables. Annual mean differences that were statistically significant from the time series at each location were then identified. So with that out of the way, let's take a look at the results. These spatial maps, an example seen in figure R1, help visualize the regional differences in various climatological parameters. Visualizing the spatial distribution of these parameters provides an insight into the global impacts of this tropospheric coupled chemistry. Figure R1 is the annual mean difference in surface temperature, with reds indicating increases in temperature and blues indicating decreases in temperature in Kelvin. The yellow dots represent areas with statistically significant mean differences. This is the same for all subsequent figures. Surface temperature represents the total effect of various sources and sinks of energy. There are a number of factors that can change the surface temperature in a region, such as cloud cover, surface reflectivity, and temperature advection. So circled in yellow, in the Southern Ocean between New Zealand and the southern tip of South America, there are increases in surface temperature of about 2 to 3 Kelvin. Circled in green, there is moderate cooling of about 1 to 2 Kelvin in the Southern Ocean between the tip of South America eastward to Australia. Lastly, circled in blue in the Northern Hemisphere off the coast of Japan, there is moderate cooling of about 0.5 to 1.5 Kelvin. To begin to understand why these surface temperature changes arise, let's look at the changes in sea level pressure. Figure R2A is the annual mean difference in sea level pressure, or SLP, with reds indicating increases in SLP and blues indicating decreases in SLP. Changes in SLP can help indicate regions in which we see the influence of dynamical changes. In the mid-latitudes and regions where there is an increase in SLP, there is more upper level convergence and descent occurring. And usually when you have more descent occurring, it reduces the amount of cloud cover and reduces the amount of precipitation formed due to more of a surface level high pressure formation. In regions where there is a decrease in SLP and there is more upper level divergence and ascent occurring, usually implying more precipitation and cloud cover. But it's not quite a linear relationship. Figure R2B shows the BWMA 1850 climatology of SLP, along with the approximate locations of the mid-latitude jets seen in green. Figure R2A can be interpreted in terms of geostrophic balance and the climatology of figure R2B. In the Southern Hemisphere, between New Zealand eastward to the prime meridian, there is a weakening of the meridional pressure gradient with an associated weakening and equatorward shift of the mid-latitude jets. Also in the Southern Hemisphere, between New Zealand westward to close to the meridian, there's a weakening of the polar low and a strengthening of the subtropical high. In the Northern Hemisphere, there is a weakening of the subtropical high and the polar low. This also indicates a weakening and equatorward shift of the mid-latitude jets, though it is to a much lesser extent to what is occurring in the Southern Hemisphere. So these SLP changes are connected to global precipitation patterns. We know that because they're connected to general circulation and therefore storm track regions. Figure R3 is the annual mean difference in daily precipitation in millimeters per day, with blues indicating increases in precipitation and reds indicating decreases in precipitation. We are interested in how coupled tropospheric chemistry influences global precipitation because not only is there a connection to general circulation, there are also influences from the microphysics of aerosols. There are significant changes in precipitation around the IPCC, circled in yellow. Just north of the maritime continent, there are increases in precipitation of up to 1.5 millimeters per day. In the eastern equatorial Pacific, there are moderate decreases in precipitation between 0.5 to 1.25 millimeters per day. This band of decrease loosely extends through the Amazon forest to equatorial Africa. The precipitation pattern indicates that the Walker circulation is strengthening, decreases in precipitation in the equatorial Eastern Pacific, with increases in the equatorial Western Pacific, though this signature does not appear as strongly or if at all, in the SLP changes. In the Southern Ocean, there is a slight increase in precipitation between 180 degrees and 60 degrees west, circled in red. The changes north of the Antarctic sea ice can be related to Figure 2, the SLP changes, where there is a decrease in the subtropical high and associated equatorward shift leading to more ascent. And in the Southern Ocean, between 120 east westward to 60 west, circled in green, there are moderate decreases of precipitation of about 0.1 to 0.75 millimeters per day. These changes can once again be related to changes in SLP, where we see an increase in SLP, with which we expect anomalous descent and less precipitation. The final change I'd like you to take note of is circled in blue off the coast of Japan, where there is a decrease in precipitation. This change seems to be associated with increased cloud cover and cooling, which is expected to reduce latent heat fluxes in this region. So now let's take a look at the change of clouds and between the two configurations. Changes in cloud fraction and the net cloud radiative effect, or CRE, have a significant influence on the surface energy budget and hence temperature. Figure R4A is the mean difference in total cloud fraction. Figure R4B is the mean difference in net CRE, given in units of watts per meter squared. For these two figures and all subsequent figures, reds will indicate increases in the quantity, while blues will indicate decreases in the quantity. The net CRE is the sum of the long wave cloud effect and the shortwave cloud effect. Positive values indicate regions where the net CRE contributes to warming, while negative values indicate regions where the net CRE contributes to cooling. Changes in the total cloud fraction are intimately related to net CRE changes, though total cloud fraction does not differentiate the altitude of clouds. So, and also low clouds contribute to negative CRE, while high clouds contribute to positive CRE, generally. If there is an increase in total cloud fraction in a region where clouds are typically at high altitudes, like over a desert, for example, this will contribute to a positive change in the net CRE. If there is a decrease in the total cloud fraction in a region where clouds are typically at a high altitude, this will contribute to a negative change in the net CRE. The opposite relationship is true for negative changes in the net CRE, as depicted on the slide. In the Southern Ocean, circled in yellow, there are increases in the total cloud fraction with associated decreases in the net CRE. In the Southern Ocean, circled in green, there are decreases in total cloud fraction with an associated increase in the net CRE. We can also see in both of these regions that sea ice is playing some role. Taking the green circle area as an example, there are increases in surface temperature in this region with associated sea ice melt, with very little changes in cloud cover. So low clouds go from having almost no effect on surface temperature to having a substantial negative change in the net CRE when there is some open ocean. The final area I'd like you to take note of is off the coast of Japan, circled in blue, where we see increases in the total cloud fraction with associated decreases in the net CRE. This area is also associated with significant reductions in surface temperature. Many of these cloud changes are triggered by changes in circulation, which we have seen in the SLP changes. CRE changes over the ocean seem to play a more direct role in surface temperature changes compared to land surfaces, which is to be expected. Though SLP changes do play a role in shaping the cloud differences, they do not capture the picture of what is happening vertically in the atmosphere. As was said, these spatial differences that were shown provide the global picture, but we don't really get to see what's happening upwards. So to help interpret these results, it is best to focus on a zonal average structure of the response to coupled tropospheric chemistry. As you can see in figure R5, the y-axis is pressure of an atmospheric layer, decreases in pressure are related to increases in the net series, and decreases in altitude. The x-axis is the latitude band, which the quantity was averaged over all longitudes. The gray dotted line represents the simplified BWMA 1850 climatology of the tropopause, and the black contours represent the simplified BWMA 1850 climatology of a quantity, and in this case of R5, that is atmospheric temperature in Kelvin. All zonal averages will have similar features, again with reds indicating increases in a quantity and blues indicating decreases in a quantity. There are decreases in temperature throughout most of the troposphere in the northern hemisphere. There is a non-statistically significant increase in the tropical troposphere. In the southern hemisphere, there is a decrease in atmospheric temperature until about 60 degrees south in the troposphere. In the tropical stratosphere, the stratosphere is above the gray dotted line again, there is a decrease in temperature. The largest difference in temperature, though, which is apparent from this slide and figure, is about 1 to 1.5 Kelvin increase, and it is seen in the southern polar stratosphere, or SPS. If the meridional temperature gradient, so the north-south temperature gradient in the troposphere decreases, an associated weakening of the polar vortex can be expected. In the southern hemisphere, the meridional gradient is decreasing due to warming near the poles. This does not occur to the same extent, or at all, in the northern hemisphere. It has been shown that the jet response to a nearly uniform warming of the troposphere results in a poleward shift of the jet. In this experiment, we have the opposite. Though I will not say it's a uniform tropospheric cooling, it is more localized than what we would consider a uniform warming or cooling, sorry. But this would still imply the equatorward shift of the jet. And this is reinforced by the warming in the southern polar region. So changes in large-scale dynamics play a key role in shaping the climate response to coupled tropospheric chemistry, as seen in the SLP changes in figure R2. Figure R6 depicts the mean difference in zonal wind in meters per second. When the meridional temperature gradient decreases, like in the southern hemisphere troposphere, a weakening of the polar vortex is expected. When zonal wind decreases, more descent is expected. This is due to an increase in baroclinicity, and as seen in the SLP changes, more anticyclogenesis is occurring in the southern hemisphere as a result of these changes. The zonal wind, just to remind you, is the east-west wind, and this quantity captures the locations of the jets. Taking note of the BWMA 1850 black contour climatology, let's look at the northern hemisphere results. We can see a slight decrease in the zonal wind north of the jet max, and a slight increase in the zonal wind south of the jet max. This implies an equatorward shift of the jet. A similar response is seen in the southern hemisphere with the two jets, the mid and the subtropical jet, though in the opposite direction. As well, the largest difference occurs in the southern hemisphere, in the stratosphere, where we see a large reduction in zonal wind of up to 3.5 meters per second. This is the result of the reduced meridional temperature gradient, weakening the polar vortex in the southern polar stratosphere. In the next few figures, I will try to unpack all of the radiative, dynamical, and latent heating differences between the models that may be leading to this response. To be able to unpack the influences to the previously seen atmospheric temperature plot, it is important to look at various heating rates. Figure 7, panel A, shows the change in radiative heating, which is the sum of long-wave and short-wave heating rates in Kelvin per second. Panel B of this figure shows the sum of the latent heating and dynamical heating rates. Latent heating changes are mainly confined to the troposphere due to the extreme scarcity of water vapor in the stratosphere. Evaporation and melting cools the surrounding environment, and condensation and freezing warms the surrounding environment. That's sort of the gist of latent heating changes. Dynamical heating changes indicate changes in horizontal and vertical advection. So when looking at panel B, we should keep in mind that any large differences in the stratosphere are predominantly from dynamical changes as opposed to latent heating changes. The main takeaway from this figure is that the radiative heating changes are nearly equal in magnitude, but opposite sign to the latent and dynamical heating changes. This is to be expected, but with the next figure, we will see that the majority of the radiative heating, panel A, changes arise from changes in long-wave emissions. As panel A has already been explained, let's just focus on panel C. Panel C represents the change in long-wave heating, which is a component of the quantity seen in panel A. Long-wave emissions in a grid box are heavily dependent on the grid box's temperature and upwelling and downwelling fluxes into the grid box. The climatology of long-wave heating is actually mostly negative, so we can really call this long-wave cooling, and that is in most of the troposphere and stratosphere, barring the area in the tropical tropopause. This means we can interpret reds as decreases in long-wave cooling and blues as indicating increases in long-wave cooling. The key takeaway from this plot is to see that the majority of changes in radiative heating arise from changes in long-wave emissions rather than short-wave emissions. We'll be able to see the short-wave changes in the next slide. Again, panel B has already been explained, so let's take a look at panel D. Panel D represents the change in short-wave heating. Short-wave heating changes indicate regions where there is more or less absorption of solar radiation by gaseous species like ozone, other greenhouse gases like water vapor, and aerosols, and clouds. The key finding here is really occurring in the southern polar stratosphere. In modeling studies, when ozone is directly modified, the majority of the temperature response arises from changes in the shortwave absorption in the lower stratosphere. In our study, we see the opposite. Shortwave heating changes in most of the stratosphere are nearly an order of magnitude less than the changes seen in panel B. And reminder, most of the changes in that region are from dynamical heating. So with this slide, we'd like to make the argument that increased ozone in the SPS is not the cause for warming, but rather is a consequence of dynamical warming. This dynamical warming in the SPS appears to arise from dynamical changes originating from the troposphere, with ozone slightly modifying the warming in this region. With that being said, the changes in shortwave absorption in the troposphere are less clear. Our current theory is that changes to various atmospheric constituents like primary organic matter, black carbon, and secondary organic aerosols, among a few, are resulting in changes to shortwave absorption in the troposphere. We postulate that the tropospheric changes in shortwave absorption potentially trigger these changes in the dynamical and latent heating rates in the troposphere, which in turn drives the long-wave cooling. In order for us to accurately assess this theory, we will need to run controlled experiments, which we do plan to do. So with the next plot, I just mentioned some of these aerosol changes. Let's take a look at them. Figure R8 shows the mean difference in black carbon. Anthropogenic sources of black carbon, aka soot, comes from the incomplete combustion of fossil fuels, biofuel, and biomass. Wildfires are a natural source of black carbon, aka BC. BC has been classified as an absorbing aerosol. BC can absorb incoming shortwave radiation and burn up clouds, also known as the semi-direct effect. The main feature of figure R8 is the reduction of BC throughout the atmosphere, with larger reductions in black carbon in the northern hemisphere troposphere. Relating this to the shortwave heating, the decreases in BC appear to minorly decrease shortwave heating in the northern hemisphere. These changes in BC also closely mirror changes in primary organic matter, which we'll see in the next slide. Figure R9 is the mean difference in primary organic matter, aka POM. POM in the context of this study is sourced largely from biomass burning. POM can act as an absorbing aerosol, but this depends on how much internal mixing occurs with other aerosols like BC, SOA, sea salt, etc. Also, when brown carbon is parameterized in these models, POM output, along with total organic carbon, is used to interpret the radiative effects of brown carbon. So there's sort of a way around to figure out the impacts of brown carbon. Again, similarly to figure R8, there are large decreases of about -30 to -80% in POM throughout the atmosphere, with larger reductions in the northern hemisphere. In combination with the BC changes, they help describe why there is a hemispherical difference in shortwave tropospheric heating. While the previous figures partially explain the temperature differences, the following figures show the main drivers of chemical differences between the models. Figure R10 is the mean difference in SOA, in kilograms per kilogram of dry air. The improvements to SOA chemistry added to WACOM 6 significantly impacts the SOA loading, especially in the tropical troposphere. In the tropical troposphere, the increase relates to about a 200 to 300% enhancement in SOA loading. Also, this figure hides the true increases in SOA in the mid to lower troposphere in the Northern Hemisphere, which are actually about 30 to 50% north of the 50 degrees north latitude line. The volatile basis set VBS chemistry that is used appears to lead to a large consumption of various radical species like hydroxyl, nitrate, NO, NO2, etc. BVOCs and VOCs also consume ozone as well, but not as readily as the just mentioned species. Reductions in these species can influence the HOX, NOx, and CLOX catalytic ozone destruction cycles. Due to the inclusion of this SOA chemistry, it appears that ozone in the troposphere and stratosphere have an increased lifetime due to reduced chemical destruction. It should be noted that even in areas where there appears to be reductions in SOA, there are likely increases in intermediate volatile organic species that are in the gas phase that are also consuming oxidizers. So this is really going to blare out to everyone. There's ozone everywhere. So figure R11 is the mean difference in ozone. As previously mentioned, the changes in ozone are dynamically and chemically driven. First focusing in on the troposphere, we can see increases in ozone throughout, except in the tropics. In the tropical troposphere, ozone is consumed by BVOC species to contribute to SOA production. Elsewhere in the troposphere, ozone is increased due to reduced chemical destruction by oxidizing species. Looking at the SPS, the changes in ozone do appear to be largely dynamically driven. Dynamical warming in this region, due to increased descent, leads to warming temperatures. These warming temperatures in the SPS mean that there are fewer polar stratospheric clouds, or PSCs. Fewer PSCs means fewer heterogeneous ozone removal reactions. And in a few figures down, we will see how the chemical species involved in these PSCs reactions are also reduced due to warmer temperatures. Though first, let's take a look at the most reactive atmospheric oxidizer, hydroxyl, which is largely reduced throughout the troposphere. Figure R12 is the mean difference in hydroxyl radical in molecules per meter cubed. There are large decreases, about 20 to 66% reduction in hydroxyl throughout most of the troposphere, with a small increase near the tropical tropopause. The reduction in hydroxyl can partially explain the increase in ozone. For those familiar with the HOX catalytic destructive cycle, seen the propagation portion of it, which is seen in the top of the slide, we'll understand that this is the method that ozone can be removed. There are more steps to this HOX cycle, but I'm just highlighting this one part of it. So if there is less hydroxyl present, then this pathway is less active. The inclusion of the VBS chemistry seems to lead to greater consumption of hydroxyl and increased lifetime of ozone. It should be noted too that the largest increase in SOA roughly matches up with the largest decrease in hydroxyl. Other species like CLOX, NOx, and HNO3 are also modified, further increasing ozone's lifetime. If needed, I do have more detailed slides describing the HOX cycle, NOx, and all these other cycles in my appendix. Figure R13A shows the changes in HNO3 in the gas phase, and figure R13B shows HNO3 NAT differences. These variables relate to the polar stratospheric cloud reactions. The key area I'd like to bring to your attention is in the southern polar stratosphere once again. Here we can see that HNO3 is preferentially found in the gas phase compared to HNO3 NAT in the condensed phase. This does not occur in the NPS, or the northern polar stratosphere, with both species being reduced. The dynamical warming in the SPS leads to warmer temperatures there. Polar stratospheric clouds form in temperatures below 197 Kelvin, with the more destructive type 2 forming in temperatures below 190 Kelvin. Due to the warming temperatures, more HNO3 is found in the gas phase as opposed to being condensed in PSCs. This reduces ozone destruction in the SPS due to fewer heterogeneous reactions. I should say, though, that this is just NAT type PSCs, but other types like the STS type of PSC, aerosol, were also reduced in the southern polar stratosphere, even though they're not shown in the seminar. A related quantity, total nitrogen, or NOY, which includes HNO3, also results in some interesting changes between the configurations. Figure R14 shows the difference in total nitrogen, NOI. The constituents are described on the top right of the slide, with the important one for this study being the organic nitrate component of NOI. In this study, unfortunately, we were not able to separate out the organic nitrate portion, but as previously stated, has been estimated to be as much as 30 to 45% of total nitrogen in certain environments. Organic nitrate aerosol, a subset of SOA, leads to a negative radiative effect at the surface. Should say though that this is organic nitrate in the gas phase. Focusing on the changes in NOI in the troposphere, there are increases in NOI throughout, with more changes occurring in the northern hemisphere. It is possible that a portion of the differences in NOI arises from the organic nitrate component. There is a strong spatial correspondence between the shortwave heating changes and the longwave cooling changes below 700 hectopascals and from 10 degrees north to the North Pole. This suggests that changes in diabatic heating are potentially influenced by increased organic nitrate in the northern hemisphere. This may influence the tropospheric cooling, which then results in those equatorial shifts of the mid-latitude jets. So just beyond the chemical and dynamical changes we've seen in previous figures, there are also changes in cloud distribution as well that we've seen in figure R4. These changes arise from and potentially feed back on the dynamical changes. Our figure R15 shows the mean difference in net CRE, with the y-axis having the net CRE in watts per meter squared and the latitude on the x-axis. Latitudes with statistically significant differences are seen in red. This is the same quantity seen in figure R4b, with positive differences contributing to surface warming and negative differences contributing to surface cooling. There is an absolute minimum in the net CRE around 65 degrees south. This reduction in net CRE is largely due to reduced sea ice around Antarctica. Immediately adjacent to this minimum, at around 60 degrees south, there's an absolute maximum, in the mean difference of the net CRE. This band of increased net CRE appears to be due to the reduction of cloud fraction between New Zealand and South America, which was shown in figure 4a, and also corresponds to a reduction, in surface winds. A secondary maximum occurs near the equator in the net CRE, and this band of increased net CRE occurs around the IPCC over the Pacific Ocean. The net CRE is largely negative in the northern hemisphere, with less variation than the southern hemisphere, though also less statistical significance in this region. While this figure does not show us what's happening in the vertical, the next one will. Figure R16 is the mean difference in zonal cloud fraction. This represents how much, on average, a grid box is occupied with clouds, averaged across all longitudes. In the SPS, there are minor decreases in cloud fraction that are partially related to the reduction in PSEs due to warming in this region. That being said, there is an increase in the lower stratosphere of about 0.02, which that increase is predominantly PSEs in the water ice phase. This increase in cloud fraction extends into the troposphere. From 80 degrees south to 45 degrees south, between 500 hectopascals and 200 hectopascals, there is a broad region of decrease in cloud fraction. This likely arises due to changes in zonal wind, which we're seeing in figure R6, combined with the tropospheric cooling. In the lower troposphere, the surface to about 700 hectopascals, between 65 degrees south and 40 degrees south, there's a decrease in cloud fraction. Weaker near surface winds in this region decrease the sea salt spray into the lower troposphere. Sea salt is extremely hygroscopic, so any reductions in sea salt aerosol results in reduced clouds. There is also an impact of the change in dynamics, which may be impacting the reduction of clouds here. This is one of the dynamical feedbacks on cloud formation. From 45 degrees south all the way to the North Pole, there are moderate increases in the cloud fraction in the mid to upper troposphere. Tannen and Kane, 2017, ran a simulation with no CCN microphysics and cloud phase determined purely from temperature with a tropospheric warming response, i.e. the opposite temperature response seen in this experiment. This resulted in a similar structure, but with opposite sign to what is seen in figure R16. I should caveat that with they had uniform tropospheric warming. We have more localized tropospheric cooling. So it's not quite an apples to apples comparison, but qualitatively, we can use it as a comparison. This is further evidence that much of the cloud structure is due to the tropospheric cooling response. Referring to the changes in shortwave heating, there is also a cooling influence of cloud in the Northern Hemisphere. The following figure, changes in the cloud liquid, also indicates an increase in cloud's cooling effect in the Northern Hemisphere. Figure R17 is the mean difference in cloud liquid amount. Changes in cloud liquid are due to a number of factors, dynamical changes, CCN changes, etc. As the changes in cloud liquid are mostly confined to the lower troposphere, the changes in cloud liquid indicate changes in low clouds' abilities to reflect shortwave radiation. More cloud liquid in the lower troposphere results in more shortwave reflection back out to space. Generally, there are decreases in cloud liquid in the Southern Hemisphere, with larger increases in the Northern Hemisphere. The decreases in cloud liquid in the Southern Hemisphere are associated with the positive change in CRE throughout most of the Southern Hemisphere. While there are reductions in sea salt aerosol throughout the globe, there are much larger decreases in the Southern Hemisphere. This is what appears to be driving many of the decreases in cloud liquid here. Increases in cloud liquid in the Northern Hemisphere are associated with negative changes in CRE throughout most of the Northern Hemisphere. These increases in cloud liquid may be partially due to increases in organic nitrates and other SOAs, though this is an area for further research. Figure R18 shows the mean difference in sea salt aerosol. Throughout most of the troposphere, sea salt aerosol decreases, with one exception being between the South Pole and 65 degrees south. What our theory is in this region, here there's a reduction in sea ice, which exposes the sea ice surface, whipping up more of the sea salt spray. The largest reduction in the figure is between 65 south and 45 degrees south in the lower troposphere. The reduced wind stress at the sea surface likely arises due to the weakened polar vortex, leading to fewer mid-latitude cyclones and more anticyclogenesis, reducing 10-meter winds overall. We do have that 10-meter wind plot in the appendix. So let's conclude all of these results, because there are many. The changes in organic nitrates may influence tropospheric cooling. These organic nitrates are known to cool the surface when they're in the particle phase. The inclusion of the VBS mechanism may increase organic nitrates and other SOA in the atmosphere. Organic nitrates' influence on clouds was not directly assessed in this work and will need to be further investigated. Reductions in POM and BC in the Northern Hemisphere contribute to a reduction in shortwave heating. The mechanism for this reduction requires further investigation, though it may be due to wet and dry deposition, or from POM/BC aerosol being coated in another aerosol type, leading them to being placed in a different aerosol bin. These changes further contribute to the hemispheric asymmetry that we see. The tropospheric cooling that occurs then results in equatorward shifts of the mid-latitude jets. The dynamical changes that result from these changes in the jets amplifies tropospheric cooling in some regions while counteracting it in other regions. The change in ozone in the SPS seems to be merely a result of dynamical warming that occurs there due to the changes in zonal wind. The zonal wind reduces due to a reduction in the meridional temperature gradient, which leads to increased descent and adiabatic warming. Ozone increases do not appear to be a major influence to the temperature changes seen, but are rather a consequence. This temperature response also acts to reduce HNO3 PSCs, which further amplifies ozone formation in the SPS. The changes in SOA in the troposphere, along with NOI, seem to be the major chemical differences in this experiment. Increased production of SOA, increased production of IVOCs, and increased production of organic nitrates and other SOA species work to consume many radicals. This pool of radicals is then reduced, resulting in a longer chemical lifetime for ozone. So there needs to be more investigation from our side into the role aerosols are playing in cloud formation and the semi-direct effect. Other parameters such as wet and dry deposition rates of aerosols were not available for both configurations. These processes will have to be explored in future simulations. We believe that a detailed HNO mechanism may provide a better representation of the hydroxyl processes, though this will have to be a future endeavor for us. Before I wrap up, I would just like to acknowledge the funding and support provided by the Natural Sciences and Engineering Research Council of Canada and from the Ontario government. I'd also like to acknowledge that the CESM project is supported primarily by the National Science Foundation, along with thanking all the scientists, software engineers, and administrators who contributed to the development of CESM2. In particular, Andrew Gettleman and Simone Tillms for providing some guidance through email. Also, Mike Mills, I have to call you out directly because you promptly responded to my questions on the WACM 6 forum. I also have to acknowledge the Digital Research Alliance of Canada, formerly Compute Canada, for providing the high-performance computer network that we ported CESM2 to for this research. I do have a number of extra variables in my appendix if anyone would care to see them. We've continued to let the model cases run, and they are at 180 years of output at this point. I performed the same analysis from year 40 to year 50 on the zonal wind and air temperature, atmospheric temperatures to determine if qualitatively the results were similar, and they are roughly similar. We will continue to let the models run until we can ensure that our analysis samples are taken from when the model has equilibrated. I have a time series of the total mean difference of surface temperature from year 1 to year 180 that helps depict this process. We're in the process of preparing this work for peer review and publication. Thank you very much for listening, and I'm open to questions now.
Noah, thanks very much. That was great. So yes, if you have any questions, please go ahead and submit them to Slido. This usually takes a little bit for them to pop up after moderation. So while we wait, I've actually got a question, or I don't know if it'll start a discussion or not, but so as you showed the dynamical heating changes and I think made a reasonable argument that this is sort of driving the changes in the lower, a lot of the changes in the lower stratosphere, including, you know, the increase in stratospheric polar ozone, sort of, I think both consistent maybe with a stronger like residual circulation, but also local warming. So I'm wondering, since the circulation, the stratosphere, the meridional part is wave driven, do you have a working idea on whether, on how maybe you are getting more planetary waves moving up into the stratosphere in the comprehensive chemistry run, assuming that that's what's going on? I guess what I'm wondering is, yeah, there's an equatorward shift of the jet, but is the jet also generally stronger or something like that? Like, do you have an idea of what may be going on there?
So I can't quite answer that question, but I would like to just maybe take a look at the zonal wind, and it would appear that overall the jet is weakening in the southern polar stratosphere. That's sort of where our line of like, okay, we have increased baroclinicity, so more sort of waviness in the jet structure, and so that is leading to more anticyclogenesis that's occurring there. So what we can tell, it seems like the jet is reducing in speed.
Cool, that makes sense. Thanks.
Cool.
Can wait a little bit longer. If anyone is shy, please go ahead and type your questions into the chat.
I can also, would you like to see those sort of updated results of what's happening in the zonal wind? That might interest you. But.
Sure, you could share that actually.
Cool.
I don't know if it's easy to jump back to the slides or not.
I should be able to. I'll just get it set up. Okay. I'll just go here. Can you see my screen?
Yeah.
Yeah. So this is the updated plot for a from 40 to 150 years. And you can see that there's sort of two things that are happening. This response is strengthening in the Southern Hemisphere, whereas we sort of lose this this equatorward shift in the Northern Hemisphere. At least it's hard to see in this figure. But what is interesting is it appears that this same sort of reduction in the polar vortex in the stratosphere of the Southern Hemisphere is also beginning to happen in the Northern Hemisphere as well. And that is sort of resulting in these interesting effects on, let's see, on the atmospheric temperature response. So where we didn't see a distinct or statistically significant difference in atmospheric temperature in the northern polar stratosphere, now when we've let the run extend further, we're starting to see a similar but less strong of a response in the northern polar stratosphere as we saw in the southern polar stratosphere. So it is sort of interesting, and that's why we think it's important that we keep on letting the model run to ensure that you know, our averages of these variables are actually capturing the model once it's equilibrated.
It's good to see that that's robust across the model length. Okay, first person, fantastic work, Noah. Thanks for presenting. And then, okay, can you provide some information on how you handled the ocean? Was the ocean initialized from the same state? Thanks.
You mean between the two? I'm assuming between the two configurations. It was initialized from the same state, and Neil was a big part of getting that spin up. And that was to ensure that we have a consistent results between the two configurations. So yes. And both oceans are they're fully coupled, and we're running prognostic simulations in both of them.
I think that's probably what that question was getting at, and that makes sense. Yeah, that's good. Yeah, with these pre-industrial control kind of type runs, there's an ocean drift, but if you start from the same place, then obviously I think you're seeing, at least with these 150-year simulations, that's probably something legitimate. Well, if folks have any more questions, we'll give a sort of last minute here for you to get them in. Take a break for just a second. But if not, we'll start to wrap up and just say, everyone, thanks for attending, and Noah, thanks for presenting. Appreciate it, and I think it's good to see some exploration of why the model's doing these different things. And yeah, let us know when this is published. Looks great.
Yeah, definitely will. Thank you very much.